Hola, my geometry friends. Here we are, lesson 8 in unit 7, our circles unit. So today I'm just going to give you a bunch of theorems and rules, kind of show you, explain how they work, do some examples, and then cut you loose to try them on your own. Tomorrow, the next lesson after this, we'll be doing some construction, so make sure you have a compass and straight edge ready for you, but that's next lesson. All right, first theorem. If a radius is perpendicular to a chord, then it bisects the chord. It'll also bisect the arc that is created by the endpoints of the chord. So what you see in the diagram here, we have our radius OD, and that radius is perpendicular to the chord. So when the radius is perpendicular to the chord, it bisects that chord. So it also is going to bisect the arc created by the points of intersection where the endpoints of the chord are on the circle. So it bisects both the chord itself and the arcs are equal. If we had extend that to a diameter, and we have a diameter that is perpendicular to a chord, it not only bisects the arcs AD and BD, but it also bisects the other parts, which kind of logically follows. The major arc, well, they're still minor arcs, but the bigger of the smaller arcs are also equal because the diameter would cut the circle into exactly half, so 180 degrees on both sides. So if AD, arc AD is equal to arc DB, subtracting those measures from 180 would leave the other bigger parts also equal. Now, this theorem can be used in either direction. Now, what I mean by either direction, if you know the radius is perpendicular to the chord, then it bisects the chord. So if you knew the radius is perpendicular first, then your conclusion will be the chord is bisected. If you are told that the radius bisects the chord, then your conclusion is that they are perpendicular, because the only way a radius can bisect a chord is that it's perpendicular. Okay, so we're going to do a proof. I'm going to show you why this is true. So we're going to prove the theorem. So we're given circle C. We're given that DE is perpendicular to AB. So that's our givens. And if AFC and BFC are right angles, what's our reasoning for that? So why do we know that AFC and BFC are right angles? Well, they're given that they're perpendicular. So perpendicular lines form right angles. All right. Now, as a conclusion of them being right angles, that means their measures are equal because all right angles are equal. And then remembering our wonderful triangle proofs, FC is congruent to itself. That is our reflexive property. And because we are in a circle, AC is a radius and CB is also a radius. So that means they are equal to each other because all radii of the same circle are equal. You have to say of the circle or of the same circle because you can't just say all radii are equal because not all radii are equal. Not every radius is the same length as every other radius. But of any specific given circle, all radii of that circle are equal to each other. And now we have two triangles congruent after we say that we have right angles. So what we're going to do is we are proving that triangle AFC is congruent to triangle BFC. We have the right angles. We have a situation here where we have angle side side, but remember we cannot do angle side side So our way around that is to do hypotenuse leg. But in order to do hypotenuse leg, I need right triangles. So a triangle with a right angle is a right triangle. So now that we have right triangles, now we can say the triangles are congruent by hypotenuse leg. And we're trying to prove that AF is congruent to BF. We're trying to prove that when the diameter is perpendicular to the chord, it bisects the chord. And now we are all set because by corresponding parts of congruent triangles are congruent, I can get AF congruent to FB. Corresponding parts of congruent triangles are congruent. CPCTC. We could do the same to prove the arcs. We could do the same kind of thing. We could use CPCTC to say that angle FCB is congruent to angle FCA. And then in a central angle is equal to the intercepted arc. So we could get arc DB congruent to arc AD because central angles that intercept equal angles are equal arcs. Or you can say DB is equal to DCB, arc DB is equal to angle DCB, and then arc AD is equal to angle ACD, and they would both be equal. So it works for the arcs as well. All right, so now what I want you to do is fill in the blanks. All right, take a moment, fill in the blanks, and then come back and make sure you did it right. Okay, if you're not sure exactly what to fill in, we'll do it together. If a diameter is perpendicular to a chord, then it bisects the chord. That's the extension that I was talking about up here, where this rule also works with the diameter. So if a diameter is perpendicular to a chord, it bisects the chord, just like the radius. If a radius is perpendicular to a chord, it bisects the chord. The perpendicular bisector of a chord always contains the center of the circle, whether it's a radius or a diameter. The segment that is a perpendicular bisector of a chord has to pass through the center of the circle. So it could be either a radius or it might be a diameter. And then in our proof, we said all radii of a circle are congruent. We can either use congruent or equal in measure or equal length. Eventually, when we get into the more of the proofs, we'll be using congruence. Okay, so solve for each of the given segments as best you can. So pause, try it, and then come back and we'll see how you did. So if you're not exactly sure how to approach this, remember that all radii of a circle are congruent. So what we can do is draw in radius AC, and that creates a right triangle. And since our radius or diameter is perpendicular to the chord, with the whole chord being 24, it's going to bisect the chord, so it's 12 and 12 on each side. So really what happens here is we have two right triangles that are equal to each other. So we can use Pythagorean theorem to find our radius length because our radius became the hypotenuse. So it's 5 squared plus 12 squared equals our radius squared. A squared plus B squared equals C squared. 25 plus 144 is 169. And the square root of 169 is 13. So our radius length is 13. So what you're going to have to get used to is when you need to draw in your own auxiliary line and where to do it. So you can draw in the auxiliary line to form a right triangle here. And since our radius was given as length 6, and then I have a partial radius given of length 3, that's 6. This side here was 3. We can use Pythagorean theorem again to solve for half the chord and then double it to get the length of the full chord. So let's use Pythagorean theorem. We'll do our hypotenuse, which is our radius, which is 6. That's the C. And then we have a leg of 3. And I'll just use letter A for the other part. So 36 equals 9 plus A squared. Subtract 9 from both sides. We get A squared equals 27. So A is the square root of 27. Now this simplifies into 3 radical 3. But that is half of our chord. So then we double it to get x to be 6 radical 3. And that is our exact value because it's in radical form, not decimal form. Our third one, we're given a diameter length of 20. That means my hypotenuse for my little right triangle here is 10. The height was 5. We can solve for x by doing the Pythagorean theorem. Ten squared is 100, 5 squared is 25, subtract 25 from both sides. Square root is 75, and that would be simplified down into 5 radical 3 for x. Okay, next rule, next theorem. In a circle, if two chords are congruent, then the center is equidistant from the two chords. If we change the order, then we could say in a circle, if the center is equidistant from the two chords, and the two chords are congruent. If you think about this, this makes a lot of sense. If I have 2 points on a circle and connect them to create a chord, imagine a piece of a stick or a piece of spaghetti that's around uncooked spaghetti, just so you know, so it's not all bendy and wiggly. I guess the stick's a better reference. So imagine a stick, like a broom handle, right? That is a fixed distance. So if I'm going to take that fixed distance and move it to a different location on the circle, so it's now over here where C and D is, if these two sticks are the same length, then they have to be the same distance from the center of the circle in order to touch the circle exactly. So as you move that stick around, if I were to take this and put it in a different spot, it would have to be the same distance away from the center of the circle because it touches the circle on each end. So if two chords are congruent, then they are the same distance away from the center of the circle, which, excuse me, which if we turn that around, if two chords are the same distance away from the center of the circle, then they have to be equal lengths. So right here, if we see that our two chords are equidistant from the center of the circle by our congruence markings, then they are the same length. And based on the rule we did on the front page, if a segment is perpendicular to a chord and goes through the center of a circle, it bisects the chord. So that means these two chords are equal length and they are both bisected, which means all of the half parts are 5, so x is equal to 5. 5 here, 5 there, 5 there, given 5 there. So both chords have length 10 centimeters, each half is 5. Okay, next rule. In a circle, congruent chords intercept congruent arcs, and congruent arcs intercept congruent chords. Because our circle is perfectly round, if I have a chord that I know matches another chord, that means the part of the circumference that they intercept has to equal as well. If the chords are the same length apart with endpoints on the circle, then the arc in between those endpoints would also be the same. So congruent chords intercept congruent arcs, and congruent arcs intercept congruent chords. It goes both ways, just depends on which information you're given first. So in our example here, since we know that chord AD is equal to chord DE, that means arc AD is equal to arc DE. So solve for x. Subtract x from both sides. Divided by 4. Now it does say find the measure of both arcs. So once we know x, then arc AD would be x plus 16. And then arc DE be 5 times x. So confirms that they are both 20 degrees. All right. Next, if congruent chords intercept congruent arcs, then congruent chords also define congruent central angles. So the congruent chord AB and the congruent chord DC created equal arcs AB and arc DC, which means they will create equal central angles, x and x. So we can do a quick proof of this one. It's been a couple questions since we've done a proof. So we know that our proofs always start with our givens. We're going to take our circle, given chord AB congruent to chord CD. We're going to prove that angle AOB is congruent to angle COD. So we're going to prove that x is equal to x. So because I have AO, BO, CO, and DO, all radii of the same circle, I'm going to use that first. So that AO is a radius, BO is a radius, CO is a radius, DO is a radius. All radii of a circle are congruent. So that gets me AO equal to BO equal to CO equal to DO. And we were already given that AB is equal to CD. So that means our triangles are congruent by side, side, side. So triangle DOC is congruent to triangle BOA by side, side, side congruence. And then we can just match up the angles by CTCTC. So angle AOB is congruent to angle COD because corresponding parts of congruent triangles are congruent. Simple little proof. Next theorem. In a circle, parallel chords intercept congruent arcs. Parallel chords have congruent arcs in between them. Parallel chords have congruent arcs in between the parallel chords. So arc AC is congruent to arc BD because chord AB is parallel to chord CD. So the congruent arcs are in between the two parallel chords. So if the measure of arc UT is 30 degrees, what's the measure of arc UV? So what we're going to do is just take our unknown arcs, label them as X, and because I noticed that VS is a diameter because it goes through the center of our circle, then those three arcs add up to be exactly half the circle, or they add up to 180 degrees. Subtract the 30 from both sides, combine the x's together, divide by 2. So we get x to be 75 degrees. That's the measure of arc UV, to answer the question, is 75 degrees. Okay, so those are some fun rules. What I want you to do is go ahead and practice these couple examples, not too long. And then there's our lesson summary. make a mental note of this page because we can use this a lot when we start doing proofs. All right. So good luck trying some of these 4 questions. Use the answer key as you need, and I will see you soon. All right. All right. Take care. Goodbye.